Welcome to the course of Digital Signal Processing. Today we will start lecture number 2 and we are going to study discrete time signals and systems. So let's have a look at the outline of today's lecture. Previously we talked about discrete time signals, operations, and we have looked at some basic signal types. For example, unit impulse, unit step, exponential, sinusoidal. We also talked about the periodicity and aperiodicity of a signal. Today we are going to talk about discrete time systems. So the most common discrete time systems are ideal delay system, linear system, time invariant system, memoryless system, causal system, stable system. And then we will talk about linear and time invariant system, in which we will discuss convolution sum. So a discrete time system is basically defined as a transformation or operator which maps input sequence values x of n is the input sequence values to the output sequence values y of n. So this is the input, this is the system transformation. It could be a scarce system, it could be a delay system, it can be multiplication system, it can be any type of a system, and this is the output. So we are mapping input values to output values. So this is input, this is any transformation, and this is our output. So representation of a discrete time system, that is a transformation that maps input sequence to output sequence y of n. So in this slide we are provided with the ideal delay system. So in ideal delay system we have x of n minus nd. So this is ideal delay system where n can have values from minus infinity to infinity, and n is a positive integer, fixed positive integer called the delay of the system. So as I've told you previously, ideal delay system simply shift the input. So whatever x of n in, it simply shifts the input sequence to right. So if nd is positive, this will fix the input sequence to right. If nd is negative, it will shift this sequence to left. So whenever there is a shift in left, it corresponds to advance in time. When nd is positive, it corresponds to delay in time. Okay. So here we have the example of moving average system. So moving average system means that we are taking the average of a running signal. So here you can see that this is a signal and this signal is moving. So what we have to do, we have to take the average of this window. Okay, so we know that how many points are there, 1 2 3 4 5 6. So it means that we need to add these samples and divide it by 6. So we have defined m1, m2. M1 is basically the starting and m2 is the ending. And summation starting from m1, minus m1 means smallest values, up to m2, and then x of n minus k. This signal is x of k, and x of n minus k means there are shifts in it. Okay, so if we expand this, so you know that this is starting from minus m1, so x of n minus m1, so this is m1 again. So it will increment x of n plus m1 minus 1, and it will go to x of n, and then x of n minus 1, x of n minus 2, up to n minus m2. So this system computes the nth sample of the output sequence, average of m1 plus m2 plus 1 samples of the input sequence. So just take an example here. For example, we want the output at n is equal to 7. So you see here 0, this sample is 0, this sample is 1, this sample is 2, 3, 4, 5, 6, 7. So it means n is equal to 7. So computing yn for n is equal to 7, here m1 is 0, this is m1 which is 0, and this is m2, okay, which is 5 because 0, 1, 2, 3, 4, 5. So what we are going to do, the output sample y of n is equal to 1/6 of the sum of all the sample routine. Why 1/6? Because these are 6 values, 1, 2, 3, 4, 5, 6. So m1 0, m2 5 plus 1, 1 by 6, and then these are samples that we will count. So this will be our x of 0, x of 1, x of 2, x of 3, x of 4, x of 5. So if you want to compute y of 8, we have to move this line to here. Okay, we have to move this line to here so that this will be y of 8. So, and if we want to keep the window of 6, then we have to move this line as well. So now we will compute y of 8 over the same window size, 1, 2, 3, 4, 5, 6, 6 samples, but now we are computing y of 8. So this is the moving average. We want to find out the moving average, means that signal is changing because the signal is moving, and we have defined the window. Whatever sample is coming in between, we want to find out the average of those samples. Okay, now we'll talk about the some basic types of systems. So first of all, we are going to discuss memoryless system. As the name says that it does not have any memory. So the output at every sample should depend on the input at the same value of n. So output at every value of n depends on the input x of n. So it means that y of 1 is equal to x of n. So here these two are same. Okay. If I generalize it, y of n is equal to x of k. So a system will be memoryless if n is equal to k. If both these are equal, so the system is memoryless. It means that output depends on the current sample only, not on the future, not on the past. So this is an example of memoryless system. We can see here the system is scarce system. The system is just taking the square of the input for each value of n. Now, so if we put the value of n1 here, the input will also be x of 1 square. So if I'm computing the output at y of 2, so the input will be x of 2. So this is a memoryless system. But what about the moving average system or the ideal delay system? The ideal delay system, which is x y of n is equal to x of n minus, let's say at nd we are taking the value 1. This is not a linear memoryless system, because if I put 2 here, here we will get x of 1. So we are computing output at 2, but input sample 1 is being used. So the ideal delay system or the moving average system, both are not memoryless. There is memory involved. Okay. Another important class of system is linear system. A system is said to be a linear system if it satisfies principle of superposition. Now superposition principle must need to satisfy two conditions, that is additivity property and second is homogeneity or scaling. So in additivity, what we do, if inputs are being getting added, okay, output must be added. If there is an addition at the input, there must be an addition at the output. If there is multiplication at the input, there must be addition at the output. So how we can verify it? So just take a look at equation 2.26a. So we are adding x1 plus x2, and then we are adding and then passing it through the system. Here what we are doing, we are adding, but we're adding after passing through the system. So if we add two inputs and pass through the system, or we pass an input to the system and then add them, it should be equal to output. So I'm going to explain with the help of example that will be more clear. In linear system, all you need to do is to check if there is an addition at the input, there must be addition at the output. If there is scaling at the input, there must be scaling at the output. And similarly here you can see that we have scaling at the input and then we are passing it through the system. Here you can see that what we are doing here, we are passing x1 through the system, then we are scaling. Here we are passing through the system, then we are scaling. These two must be equal. It means that it doesn't matter that we scale it first or pass through the system first, the output should be equal. Okay, so here you can see that this is input, this is scaling, and this is our overall input. This equation can be generalized to the superposition. These are all the additions. You can see that these are all the additions. Then the output, if there is an addition at the input, we have output, and there is addition at the output. Okay, where y, k, n is the system response to the input this. So this is the system response to the input this. Now we will consider an example. Let's see how it works. So here we have an accumulator system. Okay, this is an accumulator system. So what does accumulator system do? It basically adds all the values from minus infinity to n. So for example, we have a signal -1, 0, 1, 2. So if I say y of 1, it means that I have to add from -1 to 1. So the limits will be k is equal to minus infinity up to n. What is n? 1, because we are going to compute the output till 1, x of k. So if I expand this, this will be x of -1 plus x of 0 plus x of 1. Okay, so whatever the value is, we can add. So accumulator adds all the previous value till n. So we want to check whether this system is linear or not. So what we have to do, we have to satisfy two rules. One is additivity and scaling. So what we did, we are passing one input x1 of k through the system. So this is our system which basically add the previous value. So if the input is x1 of k, the output will be y1 of n. And second, we have the input x2 of k, the output will be y2 of n. So these are just the transformation. We have passed two different, because when we have to prove linearity, we must need to have two inputs for addition. Okay, now what we have to do, we have to take another input x3. x3 is what? x3 is the sum of x1 plus x2, and then there is a scaling with them. Okay, so now we are basically doing scaling and addition. You got the point? So here we have passed input 1, input 2, and now we have x3, that is sum of both the inputs. Now we will pass x3 from this system. The system is this. So y3 will be equal to same summation. Now at same input we will have x3 of k, which is equal to this x3 of n. So x3 of k is equal to a x1 of k plus b x2 of k. Now if I expand this summation, so x1 of k summation b summation x2 of k. So this whole thing and this thing, we can see that this was y1, then this was y2. So it means that if we have addition, so this was addition at the input, so we have addition at the output. This was scaling at the input, this is scaling at the output. Okay, so this is how you prove linearity. We first consider two inputs, we pass those input to the system, then we consider another input, that is x3, and we add x1 and x2 and say this is x3. We do scaling. Now we have done addition and scaling at the input. Now we provide that additive input to the system and check that whether output is equal to that input or not. Let's move on to next slide. Now, a time invariant system is basically referred to a system in which if there is delay at the input, there must be delay at the output. Okay, so suppose that a system transform the input sequence values x of n into output. Suppose we have a system that transform input to output, then the system is said to be time invariant. Time invariant means that it is not changing with time. Okay, it is not changing with time. If for all n naught, it means if for all delays the input sequence, so if you see here, there is a delay at the input, produces the output values this. So it means to say if there is delay at the input, there must need to be delay at the output. Okay, so time invariant, if there is delay at the input, there must need to be delay at the output. So how we can prove this, whether the system is time invariant or not? Let's have a look at the next slide. So again, this is a same system, that is accumulator, and we want to prove whether the system is time invariant or not. Basically what I do, my understanding is that you just consider an input and you pass that input through a system and then you delay it. Okay, and other time you take an input, you delay it first and then pass through the system. If both the outputs are equal, it means the system is time invariant. So it means that first we pass the input to the system, then delay it, and in second step we delay the input and then pass through the system. So it's up to you whether you want to follow this or you want to do the other way around. So this is the accumulator system. The accumulator system is this. Let me write it for you because here it is not written. Y of n is equal to summation x of k. K starts from minus infinity, goes towards n. So what he did, we took the input x1 of n and we delayed the input. Okay, so if we delay the input, you know that here if we have n here, we have n here. It means that accumulator system counts till n and we find the output at particular n. So if we are delaying the output here, what we are delaying? We are delaying the output because we have delayed the input. Now we have to delay the output and we want to see that output is same or not. So here we are delaying the output. So if we delay the output, so n will be replaced by n minus n naught and summation will be up to n minus n naught. Next, this is again the accumulator system which I have written here. Now what we have to do, we have to delay the input. Here we have delayed the output, here we are delaying the input. Okay, so we have delayed the input by replacing k with k minus n naught. Okay, so now we have to check whether this output or this output is same or not. So it looks different, but both of these outputs are same. So k minus n naught, if I replace k minus n naught with k1 another variable. So this will become x of k minus n naught, and we can replace k minus n naught with k. Okay, and we can also find the value of k. So k is equal to minus infinity. If I put k minus infinity, so k1 will be minus infinity. And if I put k is equal to n, because we have to find the limits, initially the limits was in the form of k, but here we have replaced k minus n naught with k1, so we want the limits to be replaced with k1. So it's simple, k1 is equal to k minus n naught. First substitute the lower limit of k is minus infinity, so k1 is equal to minus infinity. Then upper limit of k is n, so n minus n naught, so upper limit is n minus n naught. So we have seen that we get this expression. So this is similar to, let me rub it and just tell you. So if you see, this and this both are equal. Okay, so this is delay at the output, this is delay at the input. So this is what I told you, delay at the, this delays at the input, the second one, this delays at the output. So all you need to do, first delay the input and delay the output and check whether the output is same or not. Okay, let's move on to next slide. So here we have an example of compressor system. Y of n is equal to x mn. This is a compressor system. This basically compresses the signal. So let me just give you an example. For example, we have 0, 1, 2, 3. This is the input. If I pass this input from this system, this is x of n. Okay, so for example, we say that the value of m is 2. So 2 multiplies 0, because we have first sample at 0. So what will be the output? N is 0. At 0 we will have same thing. Okay, so y of 0 is equal to x of 0. Next will be y of 1. What is the value of m? M is 2. So x of 2. It means that whatever we have at 2 will come at 1. Okay, so this sample is skipped. We are not getting this sample at output. Okay, again y of 2 is equal to x of 4. So we don't have any 4, so output will be these two sample only. So now we have compressed the signal. We have 2 samples here. Initially we have 4 samples here. So this is our compressor system. So it's just like time scaling. Okay, if you multiply n with any number that is positive and greater than 1, we are going to compress the signal. Okay, and if that number is less than 1, we are going to expand the signal. You might have studied that in signal system as well, so I was just recapping it. So it's just like scaling, and we call it time scaling. Anyways, the topic here is to find out whether the system is time invariant or not. So what we have to do here, here's the input. The input is delayed. Okay, so we want to delay the input and check whether the output is delayed or not. So this is the system. Okay, this is our system. So what we are doing here, the output y of n result from input x1 of n can be directly computed from equation 2.1. So here we are delaying the output. Okay, what we have done here, we have delayed the input here, sorry, we are delaying the input. So x1 m, and we are delaying this, so whatever we have, we are just subtracting it from minus n naught. Okay, so we have delayed the input here. Now delaying the output by n naught sample yields. Now here we are delaying the output. So we know that when we have to delay the output, what we have to do, we have to make a change in the n. Here we have n, here we have n. If I'm going to replace n minus n naught here, we have to replace n minus n naught here as well. So if we compare this and this, these two are not equal. So here the system is not time invariant. You got my point? So let me recap it for you. Here we are delayed the input. So we are just subtracting n minus n naught. Okay. Here what we are doing, we are delaying the output. So when we delay the output, we replace n with n minus naught. And similarly, we have to replace this with n minus n naught. So these two are not equal. There is another way of verifying whether the system is time invariant or not. So there is like if m is equal to m2 and we have signal delta of n, and then we delay that signal, so the signal will be shifted delta. Now for this choice of input y of n, so for this particular, if we have input x delta of n, the output will be delta of n. But y1 of n is equal to 0 because why? Because if I have m is equal to 2, then this will be like, we do not have like, it means that we have a shifted at 1, but if I multiply it with 2, we will have 0. So you need to understand that it is possible to prove the system is not time invariant by finding a single counter example. It is not necessary to always prove that system is time invariant. We can find a single example that violates the time invariance property. For instance, a counter example for compressor is the case when m is equal to 2, x of n input is this. Because we have to verify time invariant, we said if input is this and x1 of n is equal to delta of n minus 1, it means we have an impulse that is shifted at 1. For this choice of input, output will be delta of n. But if we have this input, we will have output this. But because if I even multiply delta of n with 2, if we have this delta of n, okay, so if I say delta of mn, what will be the output? The output of this will be 1 because this is defined at 0. If m is 2, 2 multiplied by 0, this is again delta of 0, this is 1. But what about this? Delta of n minus 1. It means that we have impulse at 1. But what if I multiply this with 2? Okay. If I multiply it with 2, it becomes 0. It will become 0. Y of 1 is equal to 0 because delta impulse is not defined at 2n minus 1. It is clear that y1 of n is not equal to yn minus 1. So the compressor system is not time invariant. Let's move on to next slide. So in this slide we will talk about the causal system. A system is said to be causal if it only depends on the previous or the current values of input. So I'm going to use this notation, y of n is equal to this. So this is input, this is output. So k must need to be less than or equal to n. It means that output should not depend on any value greater than k. Okay, so as long as this is true, the system is causal. Okay, so let's have a look at the few examples of causal system. So if this condition is not true, the system is not causal. So here we can see that we have forward difference and backward difference. In forward difference we have current sample and advanced sample. In backward difference we have current sample and previous sample. Obviously because we have advanced samples, so output will depend on future inputs. So this is not causal. Here we have output will depend on current and previous. So this is okay. So even if you like solve it, y of like if I put n is equal to 0, this will become y of 0 and sorry, and this will become x of 1 plus minus x of 0. So according to the definition, this is k. K should be less than n. So here we can see that output at sample 0 depends on 1, which is not correct. So it cannot be a causal system. Whereas if we see here in backward, if I put n is equal to 0, this is x of 0 minus x of minus 1. So output depends on current and previous. So this is causal. Okay. So forward difference is not causal, whereas backward difference is causal system. Another important property of system is stability. Now a system is said to be stable, or in fact it is said to be bipostable, means that bounded input, bounded output. If input is bounded, output must need to be bounded. It means that, for example, if we are providing the input with a voltage of 10, then if a system is a scalar system, okay, output cannot go beyond 100. Let me repeat it for you one more time. If we have an input of 5 volts and we are passing that input from a system which is just a scalar system, the output cannot go beyond 25. So if the input is finite, the output must need to be finite. So this is what stable system is. The input x of n is bounded if there exists a fixed positive finite value of b of x. So what we are doing, we are saying the magnitude. In stability we are dealing with the magnitude. If the magnitude of input is less than some fixed positive value, and that fixed value is less than infinity for all n, it means that input is bounded. Now if input is bounded, the output magnitude must need to be less than by. It means some fixed value, and that by is less than infinity. So if both these condition holds, system is said to be bipostable. One more time, in stability we are concerned about the magnitude or the amplitude. Okay. Now here we have the example of in which we will talk about stability. To see this, assume that input x of n is bounded. Okay. We have a scalar system which is defined in example 2.5, and we are saying that 2.5 example the system is stable. The system is of the form y of n is equal to x of n. You can go and check 2.5. So if x of n is bounded, it means that magnitude of x of n is less than b of x for all n, then y of n is less than. Obviously, if the magnitude of this is not going beyond 5, output cannot go beyond 25. So y of n magnitude will always be equal to x of n square less than bx square. You got my point? There is a condition on input that input is always less than or equal to bx, and the system is scalar, so output should always be less than or equal to boundary condition square. Thus we can choose by is equal to bx square. So the boundary condition of output is equal to bx square. So 5 square is equal to 25. Okay. Now another example is of the other example is about the unstable system, which is given in example 2.7, and this is system y of n is equal to log 10 x of n. The system, what is the system doing here? System is basically calculating the log of the input. Okay, so how we can prove that the system is unstable? We can prove that the system is unstable because it is not bounded. If we provide x of n is equal to 0, it will give you for any value of time index at n. For x of n is equal to 0, even though the output will be bounded for any input samples that are not equal to 0. Okay, so x of n is equal to 0. This is bounded input. Okay, 0 is bounded, but output will be infinity. So this system is not stable. You got my point? If x of n is equal to 0, 0 is a bounded value. The output will be not bounded. Now, and few other examples of stability are accumulator system. So if you remember from our previous slides, accumulator system has the form, this is the form of the accumulator system. Y of n is equal to summation x of k is equal to minus infinity to n. This was the form of accumulator system. So what we are doing, we are considering the input is equal to u of n. It means that we are taking the form of accumulator system. Y of n is equal to summation, replacing input with, this is the input, replacing input with u, that is unit step, and k is just a dummy variable. K start from minus infinity to n. So here it is. So now this is our system, and we want to check whether this system is stable or not. So everybody knows that what is the maximum amplitude of unit step? What is the maximum amplitude of this signal, this u of k? The maximum, if I draw it, it is just this 0, 1, 2, 3, all are 1, 1, 1. So input is u of k is equal to 1 always. U of k cannot exceed 1. But what is output? So how I can explain you? Let me rub it. Okay. So if we calculate y of 0, it means that summation u of k starts from minus infinity up to 0. So if I expand it, we know that unit step start from 0, so we'll have only one term and u of 1 is equal to 0. So for n less than 0, the output will be 0 because there is no input. But for n greater than, we have y of 0 is equal to 1. Now what if I go to y of 1? Y of 1 is equal to summation u of k start from minus infinity goes towards 1. So this will become u of 0 plus u of 1, which is equal to 2. So we have seen that out when we are calculating at 0, we get the output 1. When we are calculating at 1, we get the output 2. It means that n plus 1. Okay. When n is equal to 0, this n is equal to 0, output is 1. When n is equal to 1, output is 2. That's why output is 1. It means that we have bounded the input. Input is always 1. But because of the accumulator system, output is not bounded. So we do not have any single choice. There is no finite choice for by. N plus 1 is less than by is less than infinity. That's why this system is not stable. And this is because of the input. Okay. The input is unit step. Okay. Unit step magnitude is always 1. But when we pass this to accumulator, the output will become 0, 1, 2, 3, 4, 5. It will always keep on increasing. So we do not have any choice of boundary. So this is unstable. So in this slide we will talk about linear time invariant system. So most of the time we consider linear time invariant system because of the linearity property and time invariant property. So it is very easy to describe or define or characterize a system if it is linear time invariant. So we can completely characterize linear time invariant system with its impulse response, because we know that if there is an addition at the input, there will be addition at the output. If there is scaling at the input, there will be scaling at the output. If there is delay at the input, there will be delay at the output. So a particularly important class of system consists of those that are linear time invariant. Okay, so here we are representing input with the help of delta impulses. So let me tell you, for example, if there is this input, these three samples 0, 1, 2, we can represent this impulse with x of 0, delta of n, because this is at 0, plus x of 1, delta of n minus 1, plus x of 2, delta of n minus 2. So this is what we have done here. X of k 0, 1, 2 running variable, delta of n minus k, n minus 0, n minus 1 as well as 2. So what we have done, we have represented an input with the help of shifted or scaled version of delta impulses. Okay, so this is just the input. This is just the input which is represented with the help of impulses. Okay, so now what we are doing, we are transforming. It means that we are passing this through a system. So if we pass this through a system, so whenever we pass this through a system, this is just the scaling. This is just the scaling. This is just the scaling. So transformation will be applied on this impulse. So whenever this is LTI system, if we apply impulse at the LTI system, we will get response h of n. So this is the response. Okay, so this is how we can completely characterize the linear system. You got my point, that first we represent input with the help of impulses, and then we pass these impulses through LTI system. This is only possible if the system is LTI. So this transformation will become this. So we got this formula of convolution. This is the formula of convolution sum. So we have the scaling, and then we have this response h of n minus k, which we get from delta of n minus k. Okay, so the property of time invariant, this is the property of time invariant. So we have seen that this was scaling at the input, we have scaling at the output, we have shifting at the input, we have shifting at the output. So we can simply say that this is the convolution formula. So if we remove this sign, we have this formula. Okay, so you can see here in this example, this is the input and this is the response to the response of the system. So we know that what we have to do, we have to consider sample by sample. First this sample, and then this sample lastly. So we see the response of, so you can see this is first sample, this is second sample, this is third sample. Okay, so we have represented input with the help of delta impulses. Okay, this was at x of minus 2, so we represented with the help of delta of n plus 2. Okay, so this is shifting at the input, and this is scaling, this is shifting, this is scaling, this is shifting, this is scaling, this is shifting. Likewise, if there is scaling at the input, there will be scaling at the output, and there will be shifting at the output. So the response was this for this input signal, but for this particular input the response will become h of n plus 2 because of this. for this response will become h of n, which is exactly this. And for this delta of n minus 3, response will become h of n minus 3 and scaled with x of 3, so negative. So here for h of n plus 2, this response is shifted to minus 2, minus 1 and 0. So you can see minus 2, minus 1, 0. So what is happening over here? This is the input, this is the response. So input is like this is the final. The input is broken into x minus 2, x of 0, x of 2. So because the system is LTI, we can tell what is the output. So if there is addition at the input, there will be addition at the output. There is scaling at the input, there is scaling at the output. So ultimately what we have done this thing, x of n, x of n is equal to summation x of k delta of n minus k. K is equal to minus infinity to infinity. So this is shifting at the input, scaling at the input, and addition at the input. So ultimately for LTI system, we know that if there is addition at the input, output will be addited as well, scaling at the output, and this will become h of n minus k, and this input will become output. So this is what we have done here. So response to the input, this can be only possible if we have LTI system, because only LTI system can fully characterize the output. So next thing is the computation of convolution sum. So when we have to compute the convolution sum, convolution is basically the formula or the mathematical way of computing the output of the system. In convolution, what we need the response of the system, which is h of n or h of k. So what we do, we first have input x of n, we transform the input to x of k, we have the response h of k n, we transform it to h of k, and then we transform this to h of n minus k. So this is h of k, this is of h of minus k, it means n is 0 here. So h of minus k means we just flipped it. So minus 3, this value will become here, and this 6 will go to here. And then, so what we have to do, convolution is the formula for calculating the output of the LTI system. We can only convolve if the system is LTI. We cannot find the output of the system using convolution if the system is not LTI. Keep in mind. So what we do, we have the input, we change its axis, we have the response, we change its axis, then we flip it, and then we slide it. So here we are sliding it. You can see here n plus 3, n minus 6. So we are sliding it towards right. Okay. So how I get to know that we are sliding towards right? Because we have n here. We have n here. Okay. So if n is 2, so this will become 5, this will become 4, this will become 3, this will become 2. Okay, so if n is, so depending upon the value of n, we are sliding it. Here n is 4. For this particular example, n is 4. So this is 7, this is 6, this is 5, 4, 3, 2, 1, 0. Okay, so in this slide you are told about the procedure of computing the convolution. So as I've already told you, like there are two steps. Number one, first obtain the input signal. Number two, change its axis to k. Number three, have the impulse response signal and then change its axis to k and then flip it. So this is number 1, reflecting x h of k about the origin h of minus k. Then what you have to do, shifting the origin of reflected image sequence, because we have to convolve. So what we do, we shift a signal to the point where there is no convolution, then we shift to a point where there is convolution, and then finally we shift to a point where there is no convolution. So let me briefly tell you how many intervals we have. So if both the signals are finite, it means x of n and h of n are finite, then we have 4 regions. Number 1 is no overlapping, number 2 partial overlapping, number 3 full overlapping, number 5 partial, and number 6 no overlapping. So on extreme left and extreme right we have no overlapping, on the boundary we have partial, and in the middle we have full overlapping. Whereas in the case of infinite sequence we have partial overlap or we have no overlap. There is never full overlap. Okay, there is never full overlap. So that was about the convolution. We will look into the examples of convolution in detail. At this point I was just telling you about the responses, the flipping, and the steps that you need to do for convolution. So I hope you got it. Thank you very much.